Hello everyone and welcome back to my channel. Today we are going to talk about geometrical elements according to ISO 1101. What are they? How can we identify them? And some examples. Also regarding the announcement, I actually have two announcements to make. The first one is that I will open a blog really soon. And the second one is that I now have access to an offline station with PCDMIS, and I will make content with PCDMIS software as well from now on. And in the future, I will have access also to an offline station with Calypso on it. So I will make content with Calypso as well. So you see guys, I will always search for different ways to improve my content, to make better content for you guys. So let's get to it. Let's talk generalities about geometrical tolerances. Through design, the parts are made with an ideal geometrical form. In the manufacturing process, due to the imperfections of the technological system, machine tool, part device, and all the other elements that construct the manufacturing process, the real part is made with form deviations that look nothing the same as the ideal part. In order to identify these deviations, we have to measure the parts. After measurements, the real surface is compared with an ideal one. We can see in the table from ISO 1101 the symbols for geometrical characteristics. These are the symbols that we are going to talk about in the future. We will take each and every characteristic to talk about and give examples on them. Here we can see how the geometrical tolerances are noted on the drawing. So we can see at A that we have the tolerance frame, at B this is the datum indicator, and the characteristics what the drawings asks from us. So here and here the characteristics and the datums are here. Also here. And at C we can have different additional indicators. Let's see some examples. So tolerance applied to multiple features like circles and surfaces. We can see here the flatness, tolerance 0.2, 6 times. So we do have 6 surfaces that it needs to be evaluated. The flatness needs to be evaluated. Also, we can see here that we have 6 circles with a diameter of 12, a tolerance of for the diameter of plus minus 0.02, and a true position, a diametral true position of 0.1 for each and every circle. Then we have multiple characteristics for one feature. We have linearity of 0.01 and parallelism of 0.06. Notice that the first one is not constrained by any datum and the second one is constrained by datum B. And also some other examples here as well. Linearity, parallelism, true position, diametral true position, according to 3 datums, spherical true position, this is regarding a sphere, and concentricity or coaxiality. So how to interpret the indicators from the drawing? The first example, if it is placed on the contour of the surface or on the dimensioning line, not the extension of the dimensioning line, at least 4 mm from this, then the tolerances refers to the profile of the surface. So when I said at least 4 millimeters from this, is at least 4 millimeters from the extension of the dimensioning line. So at least 4 millimeters from this, then it means it's a surface. Here as well, here in 3D as well, and also here as well. You can see it that it's on the surface, not on the extension of the dimensioning line. The second example is on the extension of the dimensioning line. It means that the tolerance refers to a derived element like the axis or the symmetry or the median point, and we can see here some examples. So this means that it's the axis also on 3D, and this means that it's the symmetry plane formed from these two planes, and on 3D as well. Okay, and the third example, if a modifier is specified, this one. Okay, so it also means median element placed in the second compartment of the tolerance frame. The tolerance refers to a derived element, the axis, the symmetry, or the median point again. Okay, so if you see this A, then you will also have to put the axis or the symmetry plane or the median point. So do keep an eye out for this one. Tolerance zone. So its position symmetric from the ideal element. This is if no other indication is made. The length of the tolerance zone is given by the size of the tolerance, and it is applied perpendicular to the specified geometry. Again, if no other indication is made. The size of the tolerance is given on the whole length of the surface, again if no other indication is made. So let's see the examples. So here we have a runout. Arrow orientation and tolerance zone is not constrained by anything, so the arrow orientation is not constrained by anything. You see, this is the tolerance zone of 0.1 regarding datum A. Okay, and we also have an example where the arrow orientation and the tolerance zone is defined to a theoretical exact dimension. So we do have a theoretical exact angle from the axis of datum A, and we can see it here as well. So it's constrained that it should be at this angle, and then the tolerance is applied. When indicated, the tolerance zone can vary. The tolerance zone is variable between position J and K in the given example right here. So we have 0.1 in position J and 0.2 in K position. So it's proportional to the curvilinear distance between the two positions. The next example, tolerance zone from one direction of median characteristics of the element, central point, median line, median surface. The arrows from the dimensions give the direction of the tolerance zone. So you can see here the arrows give the direction, this direction for this one, so you will evaluate only on this direction the true position, the A true position, and this one you will evaluate in this direction. So this is from a datum or from a network of elements. This is a network of elements, and you can see here that it's a true position without datums. So it's in regards one from another. The next example is tolerance given from two directions of the median characteristics. So it's also from this direction and from this direction. Cylindrical and circular zone when the tolerance has the symbol phi. Spherical zone when the tolerance has the symbol S with phi. individual tolerance zone of same shape applied to several individual elements. So as we see here, we have a flatness 3 times, one here, and one here. So we do 1 flatness, 2 and 3. So 3 flatness, 3 individual characteristics of flatness. And we also have the common zone tolerance applied to several individual elements. We can identify this kind of tolerance zone by the marking of CZ letters in the tolerance frame. So if you have this, it means that you have to make 3 surfaces, combine them, and then check the flatness of the 3 surfaces combined, like it specifies here. Also, we can see it here applied for a surface. And the last one is the unequally disposed tolerance zone. We do have the offset directions. When we have plus inside the tolerance frame, it means that it's outside of the material, and when we have minus inside the tolerance frame, it means that it's inside the material. And here we have some keynotes for every number from here. Theoretical geometric element nominal. 1 is the nominal contour of the element, of the geometrical element. At 2 we have one of the infinite numbers of spheres that define the offset of the theoretical geometric element. And at 3 we have one of the infinite numbers of spheres that define the tolerance zone. And at 4 we have the tolerance zone limits. Notice that we have 2.5 distance, right? So 2.5 distance, but from regarding the tolerance zone. But we do have here the tolerance zone that starts from the offset. So we do have plus deviations acceptance inside the material. Okay guys, that's it for today. Pretty soon I will make my first post on the blog and my first video with PCDMs. So see you guys soon.